To understand a biological population, whether it's billions of mutating cells or an entire generation of patients, researchers face an immediate problem. They must extract universal rules from a tiny, finite sample of data. Look at this image mapping Alzheimer's progression across 3 brain scans. The stark red and yellow contrasts show physical tissue degradation, but capturing the exact rate of decay across millions of patients requires turning these colors into computable data. Or consider this glowing microarray data on the monitor, where a scientist classifies tumors, a complex group of childhood cancers, by measuring the expression of over 2,000 distinct genes at the exact same time. Even taxonomic biology faces this hurdle. To reliably distinguish between species of the iris bloom, botanists must measure the precise length and width of these overlapping petals and sepals. Direct observation of these phenomena is insufficient for scientific proof. To extract universal rules from these messy, finite samples, researchers rely on a strict mathematical pipeline. This diagram shows the statistical loop. It is a formal methodology designed to bridge the gap between physical reality and mathematical proof. The process starts by translating physical attributes, like blood pressure or petal width, into abstract mathematical objects known as random variables. Once the data is abstracted, analysts process those objects using calculus and matrix algebra. Here, algorithms hunt for statistical significance, testing whether an observed pattern is real or just random noise. Finally, the numerical output is projected back onto the physical world, providing a concrete answer to the original biological question. This entire loop functions through 3 core architectural abstractions. First, random variables. Second, covariance matrices. Finally, empirical distributions. Statistical theory begins with the random variable, a concept often mistaken for a simple recorded number. A random variable is a strict mapping function. It takes an outcome from the sample space, the cloud shape of unquantified reality, and projects it. The function, x, forces the biological outcome to sit at a precise coordinate on the 1D real number line. This mapping behaves in 2 primary ways. It can step cleanly between full integers, counting distinct events like the number of defective cells, or it can flow seamlessly across decimals to measure continuous traits like height or blood pressure. Here is a coordinate plane displaying a probability density function, or PDF. Because the variable flows continuously, probability is defined by calculating the integral, the total geometric area shaded here under the bell curve, between 2 specific boundaries. To track growing probability, statisticians use the cumulative distribution function. It continually accumulates the integral from left to right. As the area under the bell curve fills in, the CDF forms an S-curve that rises dynamically, maxing out at a probability of exactly 1. A one-dimensional random variable traps a chaotic biological trait inside a measurable geometric area. However, a single dimension rarely captures fully complex biological phenomena. Real patient health is determined by a multivariate combination of factors, such as age, blood pressure, and enzyme levels, all acting on the body simultaneously. To accommodate this, the fundamental mapping function must upgrade. As shown here, instead of landing on a single line, the function maps the sample space to a 2-dimensional plane, transforming the random variable into a random vector. With multiple dimensions in play, we use joint probability, the mathematical framework required to understand the structural relationship and overlap between these interacting variables. This 3D wireframe bivariate normal distribution provides intuition for joint probability by plotting variables on x and y axes and density on z. Viewing it from a side profile creates a 1D marginal PDF. Slicing a cross-section generates a conditional PDF. The hidden mathematical engine dictating the entire topology of this 3D space is the covariance matrix. In this 2x2 matrix, the main diagonal numbers hold the individual variance of each isolated variable. The off-diagonal elements are the covariances, structural forces defining how variables move together. As they shift, they mathematically skew and rotate the adjacent 3D bell curve. Mastering the covariance matrix gives analysts the geometry needed to mathematically predict how multiple dimensions of biological reality warp and influence each other. There is a roadblock in this architecture. Covariance matrices and integrals require continuous quantitative numbers, yet much of observed reality comes in qualitative states. Whether noting an iris flower species or recording if a patient received a placebo or active drug, these traits are recorded as text. Look at this data table. The final column labels the flower species with the word setosa. Attempting to process this textual property directly in our continuous data matrix breaks the geometric models we just built. To fix this, statisticians use a workaround known as the dummy variable transformation. The process splits a text category column into separate columns for every possible state. The text is stripped away, replaced by a matrix of binary ones and zeros. This converts the qualitative state into a multinomial vector that maps out distinct probabilities. Once coerced into this binary numerical format, these qualitative states seamlessly enter the covariance matrices. This crucial dummy variable transformation mathematically coerces the qualitative properties of biology into the strict quantitative laws of probability. This brings us back to these original paradox. We have a theoretical architecture, but we only possess a finite, limited spreadsheet of actual data. Here, on this empty coordinate plane, we can map the physical data's attempt to mimic the theoretical math using an empirical cumulative distribution function, or ECDF. The ECDF plots these raw, discrete data points one by one. As the observations accumulate, they create a jagged stair-step line that climbs upward. To prove that this jagged line actually represents the population, statisticians rely on the Gliven-Coe-Cantelli theorem. The theorem continuously measures the maximum vertical distance between our jagged, incomplete empirical data line and the true, invisible theoretical curve that governs the entire population. It provides a strict mathematical guarantee. As our sample size n approaches infinity, the maximum distance between our physical sample and the theoretical truth converges, almost surely, to absolute zero. As thousands of data points flood the axis, the steps become microscopic. The jagged empirical line perfectly morphs into the smooth, continuous theoretical curve. The Gliven-Coe-Cantelli theorem provides the mathematical proof that finite samples are reliable shadows of their parent populations. When applied correctly through the entire statistical loop, probability organizes a chaotic universe of observations into rigorous geometry. The statistical loop succeeds because these architectural proofs allow researchers to calculate the properties of an unobserved population using only a measured matrix of data.